Hello everyone. Uh, in this series of videos, we'll be looking into the synchronization primitives that are available in the Linux kernel. We will start with an introduction, then look into atomic primitives, and in the subsequent videos, we will look into semaphores, mutexes, and later in the future cover things like spin locks and other locks that are provided, like maybe read-write locks and hopefully RCUs. So let's start without any delay. So why do we need synchronization primitives? Synchronization comes into play when multiple processes or threads accesses and manipulates shared resources. Allowing them without any restriction may lead to data inconsistency. Now, when I say shared resources, one thing to note here is it could be a piece of data that is being shared, like a simple variable, or it could be a critical section in code which needs exclusive access by one of the sharing multiple processes or threads. So synchronization helps to prevent the possibility of inconsistent data due to this concurrent access. It is a pretty known concept, so I'm not going to delve into the introduction and the basics a lot. Let's jump right into atomic operations. Right, so in a multiprocessor system, there are cases when resources are being shared between processes, right? In such a scenario, modification, like addition of a resource by more than one process in parallel can lead to a race condition which can result in erroneous results. For such scenarios, the Linux kernel has something called atomic_t structures. These structures provide a way to atomically modify values of a variable, which helps to remove the race condition that might occur in the previously mentioned case. So this is needed because a basic assignment or a basic increment like add can also take more than one CPU instructions. For example, an addition can be split into read, modify, and write instructions. When that happens, there's a possibility for different processes or threads to see the above addition in between one of the above split instructions. So atomic operations make sure that this does not happen. So let's jump right into the atomic structure variable that is provided by the Linux kernel. And this is the definition. As you can see, it's a simple type def over an integer which is named as counter. Right, let's so with what we're going to do is we're going to look into two different cases and then discuss how the internal implementation of these two cases and the function that atomic primitive in the Linux kernel provides and how it works internally. Right, the first one we're going to look into is atomic assignment. So what is the problem with v equals to value? What is the problem, and what is the difference between this and an atomic way of setting or doing this assignment variable, right? So as you can see, the first problem is what's called a load and store tiering. So in this, a multi-byte load and store instruction might get broken down by the compiler to process a single byte or more at a time, which leaves the single instruction non-atomic. So modern CPUs often have store immediate instructions with restricted size immediate values. For example, so which can tempt the compiler to emit a series of store immediate instructions for a larger store. Right. Another example is multiple assignments can be optimized into a single assignment. Right. And even if the programmer knows, for instance, that the variable is a hardware counter which can change anytime. So if you do have an assignment which is basically maybe inside a loop and which is updating through one single variable, compiler might optimize it and make it a single one without the loop. So this can happen because of compiler optimization. Another example of load and store tiering is older CPUs might not support what's called misaligned loads. And if the compiler isn't certain that a load will be aligned, uh, it'll have to read individual bytes, right? To solve this issue, the Linux kernel provides the atomic primitive called atomic underscore set, where you can send v, which is the atomically defined variable, and the value that you want to assign to it. Right, looking into this atomic underscore set code, it calls arch underscore atomic underscore set, which then calls the macro underscore underscore write once. Let's look into what this write once does. So this is how the code of the macro write once looks. As you can see, it also does a basic assignment, but what it is doing is it is typecasting the access to be volatile, which what it means is there will be no compiler optimization which is going to mess up the code. One thing to notice here is that the integer variable itself, which is the atomic type def variable, is not declared volatile, but a particular access is. There have been past discussions in the Linux kernel which discusses this concept of accesses being volatile and not the variable itself. The making a variable itself volatile, just like some programming languages does not make sense in most scenarios. And for Linux kernel code, what they usually encourage is to make accesses volatile where you think that kind of implementation is needed. There are some articles and discussions in LWN about this. I'll try to link them in the video description. Right, next look into the atomic addition, and what is the problem with simply doing v equals to v plus 1, for example. Right, as mentioned, it could lead to inconsistent data, because internally for a programming language like C, this could be a single instruction written in a single line, but itself for CPUs, it can actually translate into three different instructions: load, store, and load, add, and store, as we saw previously. For this, the Linux kernel provides what's called atomic underscore add, where you can send a value and the atomic variable to which you want the value to be added. Looking into the code for atomic underscore add, we see that it calls arc underscore atomic underscore add. And this is how the code of arc atomic add looks like. We can see that it's actually a set of assembly instructions. The first one is what is most relevant to us, where there is an instruction called add L, which translates to add long for the assembly language for CPU instruction. And what we also see is that that particular instruction is executed under what's called a lock underscore prefix in capital letters. This macro translates to basic lock, which is not an instruction in itself, but it is an instruction prefix which applies to the following instruction, which in our case is add L. The lock prefix that we just discussed ensures that the CPU has exclusive ownership of the appropriate cache line for the duration of the operation, and provides certain additional ordering guarantees also. In this way, the CPU cannot be preempted before the operation takes effect. It prevents other processors from writing to the same memory location at the same time. This ensures that the processor has exclusive use of any shared memory. This makes sure that the three steps that we discussed, read, modify, write, looks like a single step to other processors. In older generation architectures, the lock prefix was executed by asserting a lock on the bus, which used to come with a big hit in performance. But with new architectures, the lock is asserted on the cache lines now. This, and along with the cache coherency protocol, ensures that the access to the shared memory is managed. Let's move into our next synchronization primitive, which is semaphores. Semaphore is a good synchronization primitive for the following cases. So I'm going to stop here and try to explain a little bit about different synchronization primitives. The previous one that we discussed was basically trying to prevent access to a single piece of shared resource, which was a variable, atomic variable, an integer, right? And the subsequent one, which is semaphores and mutexes in the future, in the next videos, they are more of a lock primitive, which is used to protect access to a critical section, which could be multiple lines of code. Now, even then, different primitives in the same type and category, being semaphores and mutexes, they are supposed to be used in different scenarios, right? Semaphores are more for counting resources. Usually for the Linux kernel we have count something uh, called semaphores and mutexes are more of something where you just do protect access for a critical section, whether it could have a state of lock and unlock, uh, as opposed to semaphores, which can be 0 and 1 or more than 1, representing the number of available resources, right? So for the semaphores, the following cases is good use, where the lock is to be acquired for a long time, right? And this basic particular one is also applies to the mutex lock, but we will see in the future that there are synchronization primitives like spin locks, which are supposed to be used when the locking is needed for a short period of time, or when you know that the process taking the lock is not going to get preempted out or sleep. Even though in the modern kernel there are options of having spin locks that allow the task holding the spin lock to sleep, but we're not going to go too much of detail in the spin lock right now. But to understand that semaphores are usually for cases when you want to hold the lock for a longer time and sleep comfortably, right? And as I mentioned, as opposite to mutexes, when there is a need to track multiple resources. One more thing to note here is semaphore is based on a variable. Now this variable may be incremented or decremented, and its state will represent the ability to acquire the lock, as we will see in the further slides. Notice that the value of the variable is not limited to 0 and 1, which I just mentioned. Hence there are two types of semaphores. If it is restricted to 0 and 1, they're called binary semaphores, and for the ones that is not restricted is called normal semaphores. In the first case, the value is only 0 and 1. In the second case, the value of the semaphore can be any non-negative number. If the value is greater than 1, it is called a counting semaphore, and it's allowed to be acquired by more than one processes, which is basically equal to the count that you set. And this is what the Linux kernel provides, a counting semaphore. Now let's look into the semaphore structure as provided by the Linux kernel, and this is how it looks. It has three members. First one is a spin lock, which ensures that the access and manipulations of the member count is consistent between processes and threads. Notice that basically what this is a synchronization primitive. Inside a synchronization primitive, we will probably be covering spin locks in a different video, so stay tuned. The next member, which is count, denotes whether the resources is free or not. If it's free, it will be greater than 0 depending on what is set and how many resources are free, and if it is not free, the value of count would be 0. And the last member is wait underscore list, which is a linked list of all the threads that are waiting for the semaphore to become available. So let's look into this, how to initialize a semaphore. One of the options to initialize is this macro called define underscore semaphore, which by default sets the count to 1. An alternate to this is the function sema underscore init, which initializes and allows the caller to set count as desired. Both of the above, the macro and the function, ends up calling this macro called underscore underscore semaphore underscore initializer. And this is how this last macro looks like. It initializes the spin lock in an unlocked state and sets count to n, which you had sent. For the first case it would be 1, and in semi init case it would be whatever you have sent, and it also then initializes the wait list. Now let's move on to acquiring the mutex, which can be performed using the down function. So what I've done after this point, what you're going to notice is I've not copy pasted the entire functions because they're pretty big and I have a lot of code which might not be relevant to this kind of description that we're having right now. So I have just moved copy pasted code here which is important and relevant to keep the slides and the sections small here. So this is the most important section of the down function. And what basically this is the critical section, hence you can see that everything happening inside is under a spin lock, right? And it has basic if else check. Whether the count is greater than 0, then it's just going to decrement the count, which simply denotes that a semaphore has been acquired by the calling process. Otherwise, if the semaphore count is not greater than 0, being not available, then it's gonna call this function called underscore underscore down. Right, the function underscore underscore down calls a number of functions in between, but it ends up in the function underscore underscore down underscore common. This function is called with these two macros, one being task uninterruptible and max schedule timeout. The first one is the state which the task calling the down function would be set to while it's waiting for the semaphore to be available, and the second one is the max timeout that the task is going to wait for the semaphore to become available. Right, so looking into the underscore underscore down common function, it does two major things. Right, the first thing it does is it adds the current task to the waiting list, and then it schedules out and waits for the semaphore to become available. Right, next what we're going to look into is how this waiting list is manipulated, and to do this we have to look into a new structure. One thing to recall at this point is that this waiting list is the same one in the actual semaphore structure called wait underscore list, and the task which called down for a semaphore which wasn't available has to add itself to this list, and it does so in the form of a new structure which is called semaphore underscore waiter. And the code which it uses to add itself to the structure is this 3 lines where it adds itself to the tail. We will see later when they are picked up from the head, so this basically becomes a FIFO list. The next what we see is in the waiter.task is set to the current calling process which is trying to acquire the semaphore, and the last line is it sets this waiter.up equals to false. So one thing to notice here is the up member and that it gets set to false, and this is basically a communication in between the process trying to acquire the semaphore and the process which has the semaphore and will be releasing it. This is a way for the task releasing the semaphore to signal to the waiting tasks that some one or more resources has become available, and we're going to see this in the next slides. So now that it has added itself to the wait list, the next thing it has to do is wait. And the code for that is pretty simple. It's an infinite loop because it has to wait infinitely, and it does have a failsafe where it goes out when it has expired the timeout, or whether a signal has been sent to it to interrupt it. Otherwise, it's going to keep check doing the same thing. The first thing that it does, it sets its current state to the state which is basically task uninterruptible that we just discussed. Then what it's going to do is it's going to unlock the spin lock that it's holding, because the next step is it's going to be scheduled out and preempted. So it doesn't want to be holding the spin lock when it's scheduled down and goes to sleep. So it unlocks it and schedules itself out. Next, so when the task waiting for the semaphore is going to come back and start executing up again, when it's going to get preempted in, it's going to start by taking the spin lock again and then checking this waiter.up variable. So we will see how and when this waiter.up gets changed when we discuss a semaphore unlock. And one more thing to notice here is that in this path, the task which is waiting is gonna get the semaphore but will not be doing any decrement. We're gonna see that also why. So at this point, we're gonna jump to semaphore unlock, and we're gonna see how that affects this waiting task which is trying to acquire the semaphore. Just one thing to just keep in mind is that this check for waiter.up, and it's going to check every time it wakes up from its sleep, and if it's still false, which is the value that it's set, it's going to go back to sleep again. Right, so next let's move on to the next section, which is how to release a semaphore. So when releasing a semaphore, of the up function is called, right, and the code, the critical section in that looks very similar to the one in the down function, where everything is under that spin lock. And first it checks whether the wait list for the semaphore, and if there are waiters. If there are no waiters, then it's simply gonna increase the count for the semaphore and return. If there are waiters, then it's going to call this function called underscore underscore up. And this is the code for underscore underscore up, which is again very simple. The first thing it does, it picks up the first entry in the wait list. As you remember, the one getting added was in tail, so this is a FIFO list. It deletes that entry from the wait list, and for the dequeued waiter, it puts this up equals to true. Now this is the time to realize that one of the waiters is going to get woken up, and it's going to see that its up parameter, its up member is set to true, and it's going to basically exit the infinite loop that it had, the for loop that it had, and return with an acquired semaphore. One more thing it does is it wakes up the process so that that particular task is going to come back, acquire the spin lock, and check this wait.up. Right, so this is how this kind of handout happens, and this is also the place where you would realize by now that there is no incrementing happening in a case when there are waiters. This ties up to the fact that there was no decrementing happening on the task which was trying to acquire the lock, but it was waiting, because what's basically happening is the current semaphore that is being called up is getting transferred to the task which is waiting. Hence, there is no there's no increment required on this side, and there's no decrement required on the other side. This completes our dive into the semaphore. In the next video, we're gonna look into how the mutex works in the Linux kernel. Thank you.